What is up, guys? Welcome to another episode of CCT, and today we're going to be doing the find all numbers disappeared in an array problem. It's marked as easy, but I think getting a solution is easy, but getting this solution is hard. Getting it with no extra space and O of n runtime is tricky. And I'm going to go through a few methods of doing it. I've already thought about this problem. I haven't actually implemented it, but I've given it some thought. And so if you want this implementation, probably skip towards the end. But first, let me explain the problem for those of you who are just watching this new. So basically, you have an array of size n, whatever. Let's say it's of size 8 here. And there's supposed to be 1, 2, 3, 4, 5, 6, 7, 8 in this array in some order, but some numbers are duplicated, and then that leaves not enough room for all the numbers, 1 through 8. So what you want to do is return the numbers that are missing. So here, 5 and 6 are missing. You won't find them here because the 2 and the 3 are being repeated, thus there's no room for 5 and 6. Okay, let's go to the board. So the first way I want to talk about is if you are allowed to use, like the best thing to do is always come up with a brute force, or when you're allowed to use enough space. Let me make sure, yeah, okay. So if you're allowed to use a lot of space, how can you figure out, for example, let's use 5, 1, 1, 3, 3. What's a way you can figure out the missing values? Well, if you're allowed more space, what we can do is store maybe a Boolean vector or something for each index here. So, and we could put like false until we find that number, and then we put true. So for example, if we have 5, let's put true in the 4th index, right? Because this is 1-based indexing, this is 0. Let's keep that in mind. So we could put true here. So like we could loop through this in O of n time. And then we have a 1, so then the 0th thing we could put a true. We have a 1 again. We could just put true again in the 0th index. And then we get the 3, so we'll put a true in the 2nd index. And then once we have that, we need to return a result. So what we can do, a result of the numbers that were not in here. And so what we could do is we could loop through this and just see, for example, 1 is there. Great. So we don't add it to the result. 2, so index 1, but the number 2 was not there, so we put it here. We add it, push it back. The index, at index 2, the value, which is 3, was there. Great. At index 3 with the value 4. 4 was not there, so let's put it there. And then 5 was there. So we loop through this also, which is O of n time. And then we return this result. So let's mark down the complexity here. And this will definitely work. I mean, we managed to use space to store which numbers we had, and then we went through that structure to figure out the ones that were missing. Okay, and I think if that was the answer, this would be an easy question. So, not to say easy is easy, like Leetcode's easies aren't necessarily easy. I don't mean to ever say that these questions are easy. It's just relatively. Right, so let's do time complexity is going to be O of n, and then plus another O of n. So we'll just call that O of n time, right? Because if you do O of 2n, that's just the same as O of n. We don't care about coefficients. And then space complexity is going to be So how much extra space did we use? We really don't count the resulting thing because we needed to return a vector of ints anyway. So the space complexity here is going to be also O of n because we needed this Boolean vector of size n, as that's the data structure we use to store things. Okay, let's move on. This is the first way I thought of. I actually thought of this at first. Second way is I thought of a way to do it to cut down in space complexity but also increase time complexity. And I think this is a pretty common theme throughout most Leetcode problems. Or not that common, but like one thing that you should think of in your head in order to cut down on space complexity and maybe increase the time complexity is sorting. Does sorting put the numbers in some order such that you don't need to store things anymore in order to figure out the problem? And in this case, it kind of does. Like if we sorted this 5, 1, 1, 3, which would turn to 1, 1, 3, 3, 5. I'll write the original here. 5, 1, 1, 3, 3. So if we sort it, then what we can do is we could actually look at like the neighbors. So like 1 and like we could loop through the sorted array and we could see, okay, 1 to 1, that's fine. There's nothing missing in between there. But like we're looking for in between neighbors, which numbers are missing, because we sorted it, so we know that there's no 2 once we look at 1 to 3. There's no 2 because this is a sorted array. So when we're looking at our neighbors, we can tell that there's a missing 2. And I mean that this even works if, let's say we have 4 and 4 here, right? The only thing is, instead of 1 missing neighbor, we have to maybe loop through the numbers 2 to 4 or something so that we can push back in our vector the 2 and 3. So to summarize, we sort it in O of n log n time, which did increase our time complexity. And then we go through this in time complexity O of n time, where we look at the neighbors and see how far apart they are so that we could figure out which elements are not there. And then we add it to the resulting thing. So nowhere in here did we use space complexity. We were able to stop that by sorting stuff, which is a common theme that you should look for. So time complexity with this algorithm is O of n log n. And space is no extra space, just O of 1, constant space. And the time complexity is n log n because we sort it for n log n, and then we do this. So it's really O of n log n plus n, which then turns to that. But this is what makes it a hard problem, or a harder problem, because they say that you could do it without extra space. And this is the part, or without extra space and in O of n time, which means to me you can't sort it. Like you're only going through this array once. So that's the part that actually caught me off guard, and I couldn't do it the first time. But I've looked at the answers since, and it's a very interesting concept. I don't know how applicable it is to other problems. I feel like it's almost unique to this problem. Like, for example, the sorting to get rid of space complexity, that seems to be pretty applicable to many problems, but the way we do it with O of n time is interesting. So let me first write out. Let's just do 5, 1, 1, 3, 3, for example. And so what you do is when we do loop through this once, as the O of n would imply. Let me do it. Yeah, we loop through this once for O of n time. And then at each index, what we do is we say, okay, it's a 5. I know where this 5 should be. And if there's not a, I know this 5 should be here. And if there's not a 5 already there, or sorry, I'm skipping ahead. So what we should do is, if there was a way to turn this so that all the numbers, so like the 1 was here, don't care about that, the 3 was here, and the 5 was here, like so that if the number exists, it's in the right index. If we can make the array look like that, then what we could do is we could go through here and check, oh, does the first index equal 1? If it does, great. Does the second index equal 2? And if it doesn't, we add it to the result. Right, so we loop through this after we've done some pre-processing such that if the number exists, it should be in the right place. So the 1, the 3, the 5 are here. We don't care what ends up here. Maybe the 3 goes here, the 1 goes there, something like that. So that's the goal that we're trying to have. We're trying to put it so that every element that's there, so like the 1 is there, I just want to make sure at least one of the ones is in the correct spot, so that when I do this final loop to see which things aren't there in O of n time, I can just push back the ones where the index plus 1, doesn't equal the value that's in this array. So if you haven't thought of this yet, what we're going to be doing is swapping things to put them in the correct place. So we're going to go through here and swap things to put them in the right place. So before I do that, let's just, can I move this? No, wait. I just want to move it here or something. Yeah. Okay, so back to here. I'm going to be swapping stuff. I'm going to be going through this array. This is my pre-processing, right? And once I get to the 5, I'm like, okay, I know where this 5 should be. It should be right here. Maybe I could just swap it. Let me just swap it. So then I get 3, 1, 1, 5, 5. No. And also I knew that this wasn't a 5, so that enabled me to swap it. So now I have the 5 in the right place, which is great. It's getting closer to this, our final one. Okay, great. But now what do? Do I just continue on to the next index? No, not necessarily. What we're going to do is we're going to stay at index 0, for example, until everything at index 0 is either in the right place, or I'll tell you the other case later. So, for example, 3. 3 should be going in this spot here. And is this spot 3? No, so I'm more than happy to swap them again. And you might be thinking now, like, well, this time complexity is way more than O of n because I'm doing a lot of swapping in each iteration. You would be almost right, but again, this is why this is a bit challenging to understand. So I'll just finish off describing this algorithm here. Right, so then we swap that, and now there's a 1 here. So then I ask, okay, 1, are you in the right place? And it does happen to be in the right place. So we continue. Yeah, we continue on. And so then that's when we stop. So then we get to this one and we ask, okay, is 1 in the right place here? Is this 1 in the right place? No, it's not. It's not in the right place because this should be the value 2. So then we look, okay, can we swap it with this value? And this is where you got to think, well, there's already a 1 there, so no, we shouldn't swap. There's no point in swapping, but we also know that we shouldn't swap. I think the idea that you have to keep in mind is that we are going to go through all of these values, and we're only going to be swapping each element to the right place once. So we're only moving this 5 once. We're only moving this 1 once. We're only moving this 1 once. We're only moving this 3 once. We're only doing this once. And so that's why you can think of this complexity, the time complexity of this strategy, as we're iterating through this in O of n time. And then the inner loop, the sum of all the inner loop stuff is also O of n because it is O of n, but it's a maximum of n steps across all the iterations. So that's why it's not like O of n squared, it's just O of n. And I think we should actually write this out to understand it. Okay. So what we're going to be doing is we need to do this pre-processing first. So let's go through it. For int I equals 0, I is less than nums.size, I plus plus. And so this part is O of n. That's definitely O of n. But now what we're going to be doing is, so while this part is the tricky part. It's this inner loop is not going to be O of n because it's only n steps in total across all of these iterations. While nums at I minus 1 does not equal I, so that's saying that you are not in the right place. So for example 5, so 5 minus 1 is 4. It's saying no, this is not the 4th index. And we also have to make sure that the 4th index doesn't have the correct number. So we have to make sure that nums at nums I minus 1, so this is the 4th index, we have to make sure that it does not equal I plus 1, like the correct, or not I plus 1, it would be just nums at I, like the place that we're going to swap to does not equal that. And if you are in the wrong place, if 5 is in the wrong place and the thing that's in 5's place is not 5, then we should swap it. And this is going to be, so we're swapping U, and we're swapping U. Yeah. And this is the thing. Once 5 gets there, 5 is never moving again. Once 3 gets to its right place, 3 is never moving again. Once 1 gets to its right place, 1 is never moving again. So although this while loop may seem like it's O of something, the way that this whole thing is just O of n time is because we're only doing a maximum of n swaps. Not n swaps each time, n swaps across this entire iteration, across this entire O of n iteration. So that way we can just call this complexity O of n. We're never doing more than O of n swaps. Okay? It's kind of just like swapping at the right time. That's why we needed this while loop here. But we're really, this is the only time complexity part. We're going over O of n. Okay, great. After we get that done, then what we need to do is pretty easy. So another I equals 0, I is less than nums.size, and I plus plus. So what we're going to do here is just have a vector of int results and then say if nums at I minus 1 does not equal I, then you are in the wrong place. So then result dot push back I plus 1 because that's the value that it should be. I don't care what the value actually is, or the value in nums right now at that index is. I know that it should be I plus 1. The index plus 1 is what the value should be. And then we could just return a result. And yep. And I think this works for the edge cases because this won't go through. Edge cases meaning when there's nothing in nums. So let's try it out. I've actually never implemented this, so hopefully it works. Okay, cool. Let's throw it in. Nice. One more time, see if we could get that any faster. Okay, whatever. It is O of n time. Maybe the coefficients are making it so it's not in the 100th percentile. Who knows? Maybe the brute force is faster. It probably is, actually. But we have a lot less space complexity than the brute force way. And the brute force way I'm referring to is this way here when we store the stuff. And it's also O of n time, right? It's probably a faster O of n. Yeah. So I hope you enjoyed this video. I think the things to take away from this are that I would never have gotten this at first. I think my interviewer would have had to say, if you could put things in the right place, how would that help you, maybe? And then I would have thought of like, oh, if I could get it in this way where the value is, if the value's there, it's at the right index, and if it's not there, then it's wrong. Then I might have thought of swapping, but ultimately, like, thinking of this as O of n is very tricky. And if you guys still need help with that, feel free to leave a comment, and I will try to address that. All right, I'll see you next time, guys. Bye.